What I'm going to talk about today is a collection of 3 talks in other places. This one from Atlanta last year at KubeCon, then this one at KCD CERN, another of these KCD events, and then KubeCon in Amsterdam as well. So it's going to be a mashup of all of these, and I'm going to give you the best parts. But before that, yes, I've been contributing to Kubernetes for around, or I started 10 years ago or something, and most recently I've been looking into the access control part of Kubernetes and kind of how to make that better. If any one of you have used Kubernetes access control and have some ideas about how to make it better, like come and discuss with me, because I'm trying to improve and execute on some of those parts. Up until last week, I was at a cloud-native startup called Upbound, which has created the cross-plane project in CNCF, which some of you might know. I think at least, if I'm not mistaken, AlphaSense, I think, uses it among other people. And it's open source and a CNCF graduated project. But then in 3 weeks from now, I'll switch jobs and join AWS as a senior applied scientist. And that's basically, such that I can do this work that I'm just going to talk about, and the Cedar team there. And yes, so this talk will be about these features that are kind of coming in Kubernetes, hopefully making lives of administrators and Kubernetes users easier over time. So a quick outline. We'll go through kind of an introduction to Kubernetes authorization for those that are not familiar. And then we'll go through one of the improvements that I'm proposing to Kubernetes upstream and implementing. And then having seen that and kind of what is needed to implement some better access controls, hopefully in Kubernetes, then we take a look at, okay, so what are the fundamentals of, like, what do we need for any type of access control system, and then how Cedar policy actually basically is that piece, and how it can help us there. And then, what is next? So to really start off, if you're building an access control, access control is everywhere. You need to build it in virtually every service that you have, right? And every time you do that, you need to balance expressiveness. It's a tug of war between expressiveness on one side, and then it needs to be fast on the other side, and these are conflicting requirements. Also, it needs to be safe. Maybe you need to kind of take in some policies from potentially untrusted users and then kind of reason about them. So how do you do that? And then finally, how do you make sure that when you have a large set of policies, whatever they are, that you can actually understand what they're doing? Like, what is the intersection of all of these policies? What are they? What is happening with them then? And if you implement this yourself, you also need to make sure that this whole system, whatever you built, that satisfies all of these things, actually are doing what your thing is doing. So in the context of Kubernetes, some of you might have heard of Kubernetes role-based access control. Anyone that's used that in this room? Okay, a couple. So I'll introduce it in one moment. But basically, restricting access to the Kubernetes API, like Andre was just talking about, like all of these things that Andre was talking about, this is basically API objects and stored inside of Kubernetes, and then these are, you don't want to give anyone access to create API objects, so limiting that. Then there is a feature in Kubernetes that's called validating admission policy, and this uses a language called CEL, or Common Expression Language. It's that was created in Google, and basically it's a small expression language that looks like C-ish expressions, but without loops without any statements, just like small Boolean expressions for the largest part. But it does have loops actually. So This means that it's in general, mathematically speaking, it's not analyzable, and we'll come back to this analyzability in a moment. Then if we go even more on the expressive side, what Kubernetes supports is every time there comes in a request, Kubernetes can when trying to understand, should this user, Lucas, be able to create, say, a gateway that, Andre was just talking about, then it can actually just ask this from another service by webhooking to something else and ask, should Lucas be able to do this? In fact, I don't know. You tell me. But anytime you have a webhook of this sort, and Kubernetes is very flexible, so like you can configure it to do almost anything. But every time you add and configure Kubernetes with a webhook, then you have to make sure that that webhook is available for every single request, basically, in the API server, so it needs to be as available as your API server. You have a really hard time, if you would give users the ability to configure that webhook, then it's not necessarily fast. It's that, if your user controls it, it could block forever and never give a response, and that would mean it blocks every single request. It's not safe because it could always say yes, everyone is able to do everything, and also you have no idea what the webhook is doing because it's some like potentially untrusted code that someone else is running. So that would not be fast, safe, and reliable. So now on this scale, but then on the other hand, RBAC, the existing Kubernetes framework, is not super expressive. It allows you to make some kind of policies, but it's not like there's a bound to how much those policies can express. So that's why it's more on this side. So now the question is, is there something where we could kind of be a little bit more in the middle, like get a little bit more the best of both worlds, right? So that's the kind of the question that I set out to look at. So in every request in Kubernetes, and this actually, what I'm telling here today is, I would argue, is actually not specific really to Kubernetes in any way or almost any way, because this is basically how any API server looks. So in the request flow of virtually any API server, you need to authenticate. So you need to understand who is the user that is trying to do this request. In the Kubernetes case, it lets you use OIDC or maybe client certificates or some custom way. But at the end of the day, you get a username basically and a set of groups, right? So now, like, you know who it is, you know the actor, and you know what groups they are a part of. Great. Now the second stage is when you know their identity card, like now you need to figure out, okay, should a person with this identity be able to, perform this specific action, right? And this is, so far, it's a kind of yes/no response, like so allow or deny, right? And the built-in method of doing this is called role-based access control, right? And the attributes that anything at this level can use is basically the username. It's like a resource type. So are you creating a workload, or are you creating a secret, or are you creating maybe some policy itself? And then there are, what is the resource name, what is the resource API group, isolation boundary, etc. So, but notably, so this is what you can kind of reason about when making these policies. And notably, the request payload is not here, right? So like, if a user creates an object, say they try to create a workload, now that is not part of this place here. That comes later, at the third phase. And why is this? There's a couple of reasons, but one of them is that if you think about it, if you're trying to figure out if a user should be able to create some object, if you decode whatever they're sending you and start reasoning about whatever they're sending you before you know if they're authorized to do it, then you're actually like, maybe the answer is no, and there's a hacker that just sends you, say, tons of megabytes or gigabytes on the wire, every single request. and they have no chance of, they're not authorized at all. But the API server would kind of include that request object here and deserialize it happily and start, reasoning about it and run policy about it. That's a big denial of service vector. So there's a reason. So that's one part of the reason why there's kind of this yes/no check first, based on only the metadata and not the data, and then we proceed to kind of the third phase here. When we knew that they were kind of able to do it, then we go on, we deserialize the object, we look at it, maybe mutate a little bit, and then get the kind of final answer yes/no. And here is where what I just talked about, the validating admission policy and common expression language cell comes into play. But this is for a write request, right? And again, like this goes for some API servers. They actually merge the authorization and validating admission control phase into one. But then they have this property of not being necessarily able to mutate the request, and second, not necessarily opening up themselves to denial of service attack vector. But then on a read, there is not this third phase at all, because a read only says okay, can you read, say, a gateway within this isolation boundary, yes, no, and then whatever is there is just given to you, to the user, if the answer is yes. And what is the reason for that? Well, if you have in storage, if you have, say, 10,000 objects, it would consume a lot of memory and a lot of time to send every single object to the authorizer and say, ask the authorizer, is this object good? Is this object good? No, that object is not good. Is this object good? Etc. And that's really for large scale use cases, a really complicated thing to do and kind of non-scalable thing to do. So that's why there's not this third phase here. And again, this applies to a lot of normal arbitrary API servers as well that you would write. So yeah, Kubernetes has, as I was just telling, Kubernetes has some ways of extending, kind of writing these yourself. But the problem with having this two-phase model is that if you now wanted to say, actually I had gateway here as an example. Andrei just talked about that they used a lot of different gateway classes, and some users should be able to use maybe the internal gateway class, and some other users should be able just to actually publish something on the internet and therefore use the public one, right? Now, if that's the amount of permissions you want to give them, what you would need to do today is you would need to make first a kind of policy for the first phase, which says that Lucas can create, update, delete gateways. And then, but that's actually more than you want, because you only want Lucas to be able to create gateways with a certain property. So then in the second, third phase, you need to kind of add this deny rule, which says that actually, if Lucas tries to do anything else than test gateway, actually block him, right? And this kind of, first giving too much permissions, then just to later take it away is not very user-friendly, because even as I was writing this example, I kind of, accidentally negated myself and I was like, oh, shit, this is actually the opposite of what I wanted. Because you have to use, writing this expression is basically through the negative, right? So, yeah. So what can we do instead? What I really would like to do here is I would just want one policy which says user is Lucas, it's a gateway, and the gateway object has to have this property, namely class is test gateway. That's all I want. Those three things, and so yeah, so I started researching that a little bit some year back. And this came out of kind of looking at, like what are some unsolved problems from a, long time back in Kubernetes. I needed to write a master's thesis at the time, so I, wrote this as my master's thesis. So if you are interested in kind of a deep dive, that's 60 pages of like detail. But it also turned into a Kubernetes enhancement proposal. So that's kind of what I'm working on at the moment. So Kubernetes will actually now, hopefully in the next release, get this capability in core to be able to express this. And if there's one picture that you need to know, I guess it's this one. When Kubernetes asks the authorizer of like, should someone with this metadata be authorized? Now it's not just yes or no, but there's a mode that is called maybe, where the authorizer can say it depends. And that is actually enough to give us the capability that I was just describing of having only one policy framework for like all of the things, and not have to. Maybe as I was explaining it now, it felt complicated, and that's the exact point, right? Like it shouldn't be that complicated to express that relatively simple policy, right? Now, what is the trick to make something that seemed complicated before kind of hide that complexity from the user? And then like that trick is called partial evaluation, and we're gonna go through that in a moment. But first, a couple of use cases. So Kubernetes, you can store secrets in Kubernetes. In general, that's considered quite a like maybe not so good idea, or at least you should guard those secrets very well. And why is it not such a good idea? Because like at the moment there is no way to say that, like literally this feature, like there's no way to say that let Lucas access secrets, but only the secrets target Lucas. Something like Lucas true. That you can't do it today. So then it means that if you say give someone access to read secrets, then they can see all of those secrets within the namespace or isolation boundary, and in general, and well, unless you know the specific names and enumerate all of the names, that's very hard. So something like that, or maybe for updates, one common request is like you have an object, and again, this is like for any API server, you have the same problem, right? You have an object, and then some person should be able to update that object, but can only change some parts of the object, not the whole. They cannot, overwrite sensitive stuff in that. That should be still read-only. So that's why you need some policy language to tie the old object and the new object together and say that, like these things have to be the same, and these things you can change, however you want. Maybe you want to be able to create objects with certain names only, or node agents. Now that AI is a hot topic, you have tons of node agents doing GPU management and stuff. Like they really should be only able to do stuff that relates to their node, because otherwise a hacker or attacker that manages to escalate the privileges with one node at one node could start moving laterally to other nodes. So this is a boundary that you would like to keep. That one is basically the same as sensitive field unchanged. Or if you have something like, there was this case of like getting access to GPUs, for example. If you have an object which kind of controls GPU access and says that whoever can create this object, they get access to GPU, and then there is an admin access bool. You really want to give access people; they should be able to use GPUs, but they should never be able to set the bool admin access to true, because then they get the whole GPU. Only very few people should be able to set that admin access to true, and that's like maybe the super user. So how can we solve something like this? And it wasn't actually straightforward, and we didn't know if it was possible up until pretty recently. The trick that can be used though, and which I realized, is that there is a concept called partial evaluation, where If you have this, now this is written in pseudocode, there's no specific syntax, but if you have a policy which says something like Lucas can create gateways with this specific class, saying that in a little bit more, like formal way would be that, the verb has to be create, or like a HTTP post. It has to have this, resource gateways. The username should be Lucas. There should be a request object, and that request object's, gateway class should be this test gateway, right? And all of those have to be, satisfied. And if all of those are satisfied, this expression returns true, which means that the request can succeed, right? Now the problem was, as we said, like in in the second phase, which is doing authorization, that doesn't have the object. So how do we resolve this without the object? That's where this kind of concept of marking something unknown comes in. So if I do this request, now we can conclude that the verb was create, because I'm doing a kubectl create. The gateway API group is there. It is a gateway resource. It is me that is doing it, so that's also true. And I'm sending actually a v1 gateway object. So all of these things are true. Now as we kind of step through and had an evaluator, solve this for us. But the last one is actually, we can't know this, because like we don't have the object available at this time. We didn't deserialize it yet. It's lying somewhere in the HTTP request, but inaccessible to this process. But what we can do is a realization that, well, if this expression will return true or false, and if it returned true, then all of this would be true, and then the whole expression is true, right? But like on the flip side, if this expression was false, then the whole expression would be false, and then it would get denied. So now that we kind of folded this, and we figured out that actually we need to know this, like last thing in order to decide whether it's true or false. Then we just take this and we move it to the second phase, and then in the admission phase where we have the object, and then we resolve it. On the flip side, if there was an attacker or whoever, a user that was not Lucas, that did exactly the same request, the same everything, now we would say that, okay, the verb is create, that's true. The API group and resource matches, that's true. But now the predicate here is that username is Lucas, and now in this case, say that username is hacker or something like that, or Bob. That would be false, right? So now, using the rules of logic, we can say that no matter what this thing on the bottom is, there is no way that like whatever the object is, it cannot make this whole expression true anymore, because false and whatever is false. So this means that we can deny the request without ever getting to the object and deserializing it. So that's why how we could prune all of the stuff that is kind of bogus requests. We don't have the denial of service vector. We prune those, and only if it happened to be like I showed here, then we decode the object, we go further, and then we resolve the last one and make it such that the last kind of resolving this is equivalent to having solved it in the first place. So that's a new Kubernetes feature. Basically, the expression that we saw below turns into a condition, which is basically some opaque string that returns, that kind of takes in the request or the new and the old objects, however available. It may have a specific type, like common expression language, Cedar, open policy agent, or similar, or anything else you assign the meaning. It can be allow, deny, or saying like no opinion. So which means that just consult the next authorizer, and that's kind of like whenever this condition returns true, how should we what should we assign? What meaning should we assign to it? And then just an ID to this. So what it looks like in practice is that we go through the authentication phase, we go through the authorization phase, and now the new thing is like the authorizer can not only do allow, deny, it can also return a set of conditions and say that these conditions need to hold. I'm not sure about should I like allow or deny this request now, but I'm sure that if these conditions later are true, like they hold, then like call me back with the data and I'll tell you more. So it returns the conditions. Now the conditions, or it can return deny and then it denies here. Now the conditions are passed here with the request, and in the third phase, then it basically the authorizer gets a callback with like, here are the conditions you left me with last time. Now actually here are the objects, the old and the new one. Like now you can resolve that into true or false necessarily, and now we will actually be able to give allow or deny, and then based on that it either gets denied or goes to storage. So that's how we are able to and to the user it now just is uniform. Like they can write one policy which is just like Lucas gateways, and this field has to be set. And then I don't need to think, the user doesn't need to know what is authorization, what is admission, like all of these things that they had to kind of understand before. So that's the idea, and to make it even kind of hopefully better, let's see if we have time to go through this and if people are interested, but this is what it looked like before. So like for metadata, we could authorize both reads and writes using the RBAC mechanism. But then for data and writes specifically, we could use the cell or validating admission policy. And then there was actually this another third method in authorization in Kubernetes, which you could do reads and data. So like this kind of label selector thing with secrets, for example. But again, like these are three different paradigms, potentially three different languages. Can't we make them just one, right? Such that you have one, expression language through which you, are able to kind of talk about all of the possible modes. And again, like actually, all of the things again that I've said so far isn't specific to Kubernetes. You would need to do this. You would need to solve these problems somehow in your API server as well. So how do we express these policies, especially given that the slide we just saw? It's really, like, it seems easy at first. If you start making some access control stuff, it seems easy at first because, I'd be thinking that, like, okay, the only thing I need to, I write some code to do access control, and the only thing I need to care about is, can this user do this action on this resource, right? And then that will be yes or no. And then if it's no, then I throw them out. And if it's yes, I proceed. But that's just the kind of the tip of the iceberg. Then you might start thinking, okay, well, I have all of these whatever policies, and now I'd actually be pretty for an audit, be pretty interested in okay, Lucas, that's a sketchy guy. What can he do really? Like how far? What can he see in the system? What would the blast radius if that person got compromised be for the whole system, right? And not just what could Lucas do directly by doing some commands, but what would Lucas be able to do indirectly, right? So like if Lucas had access to use some other service, some root account or some kind of jump box or something else, maybe he would be able to impersonate something that could have even more privileges and step through that if you kind of think like a hacker. So kind of these two together, not just like what are my immediate permissions, but what are my derived permissions because with what I can do. So like an example from Kubernetes, and this is a feature, but it's kind of a security-wise a little bit interesting feature. If you have thought about it, if you create a workload in Kubernetes, then you can refer to secrets, right? you can say that create this workload and mount this secret into the workload. And when you're doing this request, when you're creating the workload, the pod or deployment or whatever, it actually never checks if you have access to that secret that you're mounting in, that you're referring to. So you can be like, damn it, I don't have access to this, like crown jewel of the company, but I can create a workload in the same namespace and just tell Kubernetes to give me the secret. That's a and this is a feature, right? But it's one that people don't think about so easily, or yes, it's in the docs, but it's not something that you think about as you're applying things to the and using it day to day. So that's so in no audit it would show up that Lucas can read secrets, which I in fact can, because I could create a workload which gives me the secret. Or what we just we're talking about was this kind of, okay, we have a request and we want to block it as fast as possible if there's no chance of that user becoming authorized ever, right? Like then we want to cut it off before doing unnecessary work or spending CPU cycles on memory or whatever. So how do we reason about that? Then the other way, right? Like you have this crown jewel of the company, like a really sensitive resource. Do you know who has access to that, either directly or indirectly, right? Like can you find that kind of attack path from your policies? And then talking about the policies, if you refactor your system, right? Like if you have one set of policies in code or in some declarative, like language, DSL, and if you one day were like, oh, this policies now really got out of hand, like I can't keep up with this anymore, I have too many, I need to restructure them in a way that I can understand. Now that is some of the scariest things you can do, because like now either you refactor something and then it goes, you give people too little privileges and then it's an availability issue, or then you give them too many like privileges and then it's a attack vector for someone that shouldn't have those. But this actually, like, if you restrict the policy kind of syntax a little bit, you can actually decide this question. You can ask, and you can answer that, well, this policy set of policies is exactly doing the same thing as this other set of policies, like mathematically for every single request that you could think of for an infinite amount of objects. So that's possible, and we're going to go through how you do that. And then there's also like, okay, you have maybe conflicting policies. Some policies says allow, and some policies says deny, and they kind of what should really happen here, like. So should everyone need to be building this access control engine, whether you build it in code or through some other language? Well, I hope not. Like, it's a lot of work. It's what people call undifferentiated heavy lifting, right? Like if you need to get it right, and you need to spend a lot of time doing it, but it's not really like maybe your company's main source of revenue. So why not do the same as Kubernetes, which had the same unifying process and potential 10 years ago, right? Like before Kubernetes, people were writing like their stacks from like booting the server to the UI, managing the dashboard, all by themselves or mostly by themselves, right? You didn't have this kind of shared glue in the middle. So every company had to do tons of duplicated work, right? Now, yes, that's still the case today, like to some degree, but at least people can kind of use Kubernetes in between, which is like, okay, it takes away some of the complexities, not everything. It's not a silver bullet, but it takes away some of the distributed systems complexity in between, and gives you some primitives such that, okay, you still need to boot the machines and whatever, but once you did, you could install Kubernetes, and then on top of that, you would have an API that is compatible for the rest of the people on top. So that's basically what is, and with the risk of this XKCD, that's basically what is Cedar. So Cedar is another cloud native computing foundation project. which provides both a language, a declarative language, and an engine for use in your trusted computing base. So it's open source. It's you can go to GitHub and get it. It supports relation, role-based access control, attribute-based access control, and relation-based relation-based access control. Then it's rock solid. I'll get into this in a moment, but when we were talking about the correctness piece, this has actually proven, its code is proven to be correct, and like satisfy the guarantee, like the semantics that you want to have in this engine. And it comes out of AWS, but it's donated to CNCF for vendor neutral governance and a kind of project. And well, it's in this team and this community effort that I'll be working, or I actually am already doing this stuff, not at AWS, maintainer and stuff for Cedar, but now I'll join and double down on that, get more days in the week dedicated to this. So for formal verification, there is kind of a small core of Cedar. At the time of this paper, there was like 1,600 lines, maybe 2,000 lines in Lean, written to kind of to implement Cedar, the specification in the language, the specification and the kind of language to actually build something that gives you allow or deny, and that's an order of magnitude less code than the production-ready Rust implementation. So like they have two implementations of this, and one of them is proven to be correct, and then they test them against each other. So like they generate millions of random unit or integration tests. They run them against both engines, and then check that they actually match. So that's what formal verification means in this context. But also has a couple of other nice features. So it's completely flexible. So you define kind of a type system. So you tell that I have a users table, I have a a documents table, and I have folders table, and these objects relate to each other in this way, and this kind of stuff. And once you declared all of that, so here I declared some like Kubernetes deployment, then actually while writing in VS Code, you actually get the autocomplete stuff saying that okay, this is a deployment, so it has these fields, right? But also if I now on purpose I misspelled something, then it says, well, you misspelled namespace. This policy is invalid because kind of like Andre was talking about, like these kind of silent things of like if you have policies which are just like there and blobs, and maybe they're doing something, maybe they're actually not. But here actually you get a clear message of like, are they or are they invalid? Then analyzability. So like this is something we talked about in the beginning, but I didn't really say what it means. Now this is what I mean with it. If we're talking about this refactor part, then in order for these two circles are not equal, right? I think we all can agree that they are not exactly the same. But how do we mathematically reason about whether they are the same? Well, if they were the same, there wouldn't be this space here. There wouldn't be this where you were in one of the circles but not within the other, right? And there wouldn't be this space here where you were within the old one but not the new one. Because if they're equal, this doesn't exist and this doesn't exist. So in order to prove that they're the same, you set out to ask, is there something within the new circle that is not within the old one? And that's how you find this one. And that's a search problem, right? You search for this one, and if you conclude that there is no such thing, where you would be part of this one but not that one, then you do the second, like the opposite order. You ask, is there something in the old one that is not within the new one? And if you conclude that that is also impossible, then you have proven that they are the same. So even though these expressions talked about infinite domain of objects, and the same thing logic you apply to, for example, if you have a deny rule which is larger than an allow rule, then the allow rule in Cedar denies are stronger. So then the allow rule wouldn't do anything. So it's just dead code. So probably you should remove it, or then maybe something you were, as you were making them, you didn't think about something, and that was actually an error on your part. Or same thing, like you have an allow which is strictly larger than another allow. Now, the middle one is not doing anything. Was that a logical error? Like, did you mean to do that, or what was the kind of story there? Or you can also just kind of reason about, like, is there a policy that you wrote in a contradictory way, where you said, username has to be Lucas, and then username has to be Bob. Like that can never be true. Like, no matter how you would choose requests. So like, then, and that sounds silly, but actually I managed to do this, a couple of times. And as I was preparing for the KubeCon Atlanta demo, we actually did exactly this, and we're like damn it, like we probably spent an hour, and we had misspelled, we had misspelled one of the names, and then when we were talking about the old object, we should have been talked about the new object and vice versa, and then like it was, you could statically know that it was always false, but we thought it did something, and then like it tricked us up. So like it kind of sounds silly, but it's super useful actually. And this kind of, that I was just talking about, like, how do you do this in this, like what can Lucas do, or, who can access this resource? So let's go through one of that example as well. So if we have this example where, like, Lucas can only write secrets with type TLS, then we would say something like, okay, the principal is a user with username Lucas, the action is create update, the resource is a secret, with a type field, and the type field is TLS, right? So that's the expression. Now, if we have a specific secret that we're really, like, we really want to keep in check, like no one should really have access to this, right? Then we can say that now the unknown thing in this expression is the principal. We don't know who the principal is. So we keep that unknown, and every time we see something, an expression which is referring to the principal, so the user, then we just we don't evaluate it. So the first thing is like, okay, principal is user. We don't know this because we don't know who the user is or who the principal is. But we know that the action is a create or update because it's a write, because that's what we're interested in, like who can write this secret. Now we know that the resource is a secret, so that's true. So like these two are true. We don't know, like what is the principal username, because the principal is unknown, but we know that this resource has a type field, and we know that this type field actually is TLS, for example. Now, because with the same logic as before, because everything else is true, and only we have something that is unknown, which can be true or false. Now, if those things that were unknown to us would be true, then this policy would apply, and then they would be able to write the secret. So we return that if there's a user with username Lucas, then they can write. And that's how we know, kind of symbolically or logically, that Lucas can write the secret. And then we can run this expression against all of our users table, and then we know, okay, it's Lucas and it's Bob and it's Alice that can do this, if it's talking about groups or something like that. So while I was at Upbound a year ago, I made this GitHub implementation of taking Cedar and applying it to Kubernetes, such that you can have unified policies like this. And basically the same thing as we saw before. It works as an authorization plugin. It returns yes or no, or then some conditions, and then Kubernetes enforces those conditions, and then you have kind of one language to talk about them, but talk about all of the things. So, for example, like write and list secrets would be able to do in the similar way. Lucas can create an update when type is this, or Lucas can list and watch when the type is this on the old object. How we would look, for example, is like if I try to do something that violates this policy, it says forbidden, and otherwise it lets the request go through for writes. Or then for reads, it would same thing, say that okay, I'm forbidden to list secrets in general, but if I limit my if I limit my read to only the basic auth ones, the basic or auth or TLS secrets, then I can see that subsection of the secrets. So I can't list all of them, that's why I get denied first time, but if I limit, I can see that's a kind of subset. So, yeah. Conclusion and next steps. Basically, the way I'm thinking about Cedar is as a kind of intermediate representation language, or kind of intermediate representation for access control. So same way as Kubernetes, like you don't have to write it all from the kind of booting the server to writing the UI. You have something in between that kind of helps you along the way. Again, it won't do everything for you, but some part of it in the middle. And now you don't need to force your users to write Cedar like you just saw in the examples. You can still have some JSON or whatever more high level thing that is applies to your use case. But then you take this more high level thing and you kind of compile it down into Cedar, and then you can analyze, like we just saw, like are these policies now equivalent? If you like combine them, are they contradictory? All of these things, and at this layer you have all of the good tools that Cedar provides you, like validation and linting and these kind of stuff. So that's kind of how I'm thinking about it. For the Kubernetes feature itself, which is kind of built on top of this idea, but it's not specific to Cedar, it's full general, it can be used with any other stuff. You can join the kind of special interest groups in Kubernetes that is talking about these. We have weekly and bi-weekly meetings. There is the proposal, Kubernetes enhancement proposal, 5,681. There's a couple of them. Like you can try out the mentioned projects, or like talk to me. I'd be happy to hear your like what's the pain points of you if you've been using some of these systems in Kubernetes or outside of Kubernetes. Like I'm interested in access control in general. This was just like one of the places that I'm applying it. And yeah, then when this kind of foundation is settled, then we can move on to work on even kind of more impactful features of this kind. So thank you very much, and let me know if you have questions later.